So let's take a look at one of these stub matching problems that we laid the foundation for in a previous video. So here it gives us an antenna with an impedance of 40 plus J 30 ohms is to be matched to a 100 ohm lossless line with a shorted stub, and it asks you to determine the required stub admittance, the distance between the stub and the antenna, the stub length, and the standing wave ratio on each segment of the line. So the way we approach these problems is as every other problem we've done. We start always with the normalized impedance, the S circle, the normalized admittance. In this case, as I mentioned in the previous video on the basics of stub matching, we use the admittance because these circuits are, or these lines are in parallel, and when we have parallel things, we can work with admittances linearly instead of having to deal with, strange relationships in terms of impedances. So, what do? How do we start? We always start, like I said, we start with ZL normalized is going to equal ZL over Z naught. And so this is going to be 0.4 plus J 0.3 ohms. At the same time, we can calculate YL normalized. And to calculate YL normalized, it's just going to be Z naught over ZL, since Y is just the inverse of Z. And so this is actually going to be 1.6 minus J 1.2. So now let's go ahead and plot ZL on our Smith chart, and we'll draw our S circle. So I've gone ahead and done that. So, again, the procedure for this is just plot ZL, run a circle centered about the origin through ZL with the radius that is the distance from ZL to this origin. Like I said in many other videos, my radius or my circle might be off by a little bit. That's just because I have to do this thing on a computer and I can't use the compass. If you use a compass, your circle should be perfect, or as close to perfect as possible. So here we have ZL, and I've labeled ZL. But we also have this point YL, and I said that we deal with YL in most cases. But to get from ZL on the Smith chart to YL, I believe we did this in a previous video. If we haven't, then we can look at it right now. Essentially, all we do is we run a line from ZL through the origin, and we intersect it with the circle on the other side. Okay, so I've drawn a line through ZL, through the origin, and now it's coming out the other side, and there is a point here of intersection with this chart, and so this point here should be YL. Now if we compare this to our actual value, it might be off by a little bit. I think the one we have on the Smith chart is about 1.58, but again, that's because my circle is slightly off and not perfectly centered. But if you're doing this on a Smith chart with paper and a compass, your YL that you get here and the YL you calculate should be identical, unless you've done something wrong. So we have ZL, we have YL, so right away we can find the required stub admittance by going through the process outlined in the stub tuning video. If you haven't seen the stub matching, or the stub tuner, I guess you can call it, shorted stub tuning method approach to impedance matching, I would highly recommend you take a look at that video before watching this one, because if you don't, none of this will make very much sense. So I mentioned in that video we have a r equals 1 circle. If you haven't already figured out where the r equals 1 circle is, it's this circle that I'm highlighting right here with green. So this circle is r equals 1. And if you recall from the definitions that we had for impedance matching and the having the input equal Z naught, and then we wanted the whole thing dividing so that it would equal the characteristic impedance, we ended up with Zn equals 1, Z naught equals 1. These such conditions exist at this point here and this point here. So the steps then are to draw your S circle, well, plot your ZL, find YL, plot your S circle, plot your r equals 1 circle, find where the S circle intersects with the r equals 1 circle. Well, I should point out that in the cases that you're dealing with impedance, this circle is called R equals 1. In the case where you're dealing with admittance, it's usually called G equals 1. These are just conventions. The circle stays the same. The circle does not move. The circle does not change. It is the exact same circle. It's just in terms of variables, because technically they're not the same variable. So what I'm going to do is I'm going to define this point at the top as A, and I'm going to define this point at the bottom as B. Because when I refer to these points later on, it'll be really simple to actually see what's going on if I do actually define these points earlier on. Now what do? What I'm going to do first is I'm going to run a line from the middle through A, and I'm going to run it off the chart. I like to extend my lines past the chart as opposed to just stopping in the middle. This is easier usually when you're calculating distances. For example, if I wanted to find the distance from A to like YL for whatever reason, I find it easier to visualize traveling along the outside of the chart like this, between lines, as opposed to trying to look through the middle, because I find it's really hard to focus with all this crazy stuff going on the inside. So I guess it's a good practical rule to just, extend your lines off. At least the lines you'll be using. Like the line for ZL we might not be using that much, so I guess that might not be important. If you have a ruler, I guess you can run through the entire thing. So it's really up to you though. But for me, you'll notice that all my lines will always run off the Smith chart, and that just makes it easier for me to actually see what's going on. So then we have another point here. So that's A and that's B. So these are my lines for A and B. If I actually zoom in there, you can't really see it because, again, the lining is kind of thick. What you'll find is that this intersection here is going to be 1 plus J 1.04 approximately. So what I'll write is at A, Y, what do we want to call it? We can call it, well, let's call it Y then, because in general it is Y, plus J 1.04. And then at B, y equals 1 minus j 1.04. Now this sort of conjugate symmetry between these 2 points will always exist. The reason is this S circle is always a circle, therefore it must have an equal radius, and this distance must be the same. This 1 is also a circle, and so these 2 points must be the same at the top and at the bottom. So if you don't have these same points, if you have like 1.5 and 1 all of a sudden, you've done something wrong, your circle is not drawn properly, go back and check it over. If it's off by like 0.01, 0.02, I'd say even up to like 0.03 or 4 maybe, you should be fine. But still, I would check your circle if the numbers are not almost identical to each other. So we've done A and B, we have YL. Now what do? The thing that we're concerned with are these reactive parts. So I'm concerned with this J1.04 and this negative J1.04. So these highlighted things I've done here are the points that I am interested in, because these things are actually going to be the admittance of my stub. Because we said we matched this part, that's fine. We matched the 1 because if you remember, if you divide by the characteristic impedance or admittance, you're going to get 1 for the real part. But we want this thing to go away now. And this is a condition, again, of impedance matching that we talked about in the previous video on single stub tuning matching methods. So what we want now is I want to take this point and I want to essentially project it onto this circle here. So if you go ahead and do that, well, that projection was probably pretty bad. I said it was 1.04, so it should be about 1.04. If this thing here is 1.1 and this is 1, this thing's 1.05, so I guess 1.04 would be just about there. So a little less than half there is going to be 1.04. And I'll do this one in a different color. And what we call this point here, and this might seem a little counterintuitive, but we call this point B prime. Okay. Now B prime, the easiest way to notice is that B prime is on the opposite side of B, A prime is going to be the opposite side of A. So I'm going to do the exact same thing at the bottom. I'm going to find 1.04 along this bottom circle, and I'm going to mark that right along the edge of the Smith chart circle here. So that, I guess, looks like it'd be close enough. So what we can call this point, we said this A prime, because it's opposite of A. So if A is on the top, A prime's at the bottom. If B is at the bottom, B prime's at the top. So what else do we have now? What do we want to do? We have to run lines through here as well, because when we're going from one point to the other, it's always easier to see if you have a line running through it, as opposed to just trying to eyeball where the actual thing is. So again, run a line off of it, and make sure, again, it's off the edge of the Smith chart, because that's just the way I like to do it. And I'll do the same thing from the origin through this point. Okay, so now we start finding our lengths and such. But I think we can actually solve this part before that. So yeah, part A asks for the required stub admittance. So the required stub admittance we're going to call ys. This thing here is essentially ys. So we're going to say that ys normalized is going to be plus minus j 1.04. Okay, so then ys, and here's where a lot of people will make a simple mistake. The most common thing to do here would be to multiply this by 100. But realize that that is the characteristic impedance and not the characteristic admittance. The characteristic admittance is 1 over 100 plus minus j 1.04. And then so you'll find that ys is going to be plus minus j 10.4 millisiemens. Don't forget your units. So this is ys. Okay, so we've done the first part. Now we want to find the distance between the stub and the antenna. So this is essentially, we're going to start from our load, and we're going to find the distance from the load to point B, and then the distance from the load to point A. Because of the symmetry of these circles, there are 2 points where we can place the stub. Typically in practice we would use the point that is closest. Usually that's just easier to deal with. But sometimes what happens is, the circuit might call for something a little abstract or something, so you might need to go further away because closer to the actual interface might be, something else going on there. So another thing to note is that we start from here. Whenever we're going for the load, or from the load, I should say, we consider YL, because if you remember, we're talking about admittances in this because it's in parallel. So we start from YL. So this is our starting point for any distance from the load. How far is the load from this? How far is the load from that? Always start at YL when dealing with these problems. In the regular Smith chart problems, we deal with impedances. We have load impedances. We start from ZL. In this case, we start from YL. So if we just look at, well, let's get rid of this little bit here. This distance here from YL to B, we defined as LB. And now the distance from this load to A, we can draw, I guess, outside here maybe. So I'm going to go all the way around, and I'm going to go to A. I'm going to call this LA. Okay, so LB is relatively simple to find, I guess. We can probably just read that off right away. So this distance we can subtract. So I guess this point we can call 0.33, that's 2, 4, 6, 7. Let's call it 0.337 lambda. And this point we'll call what? 0.3, that's 2, 4, 5. Let's call this 0.3, we said 0.3, that's 2, 4, 5, 0.3, 0, 5, because that's about halfway between 0.3 and 0.31. Okay, so now LB then, LB is going to equal 0.337 minus 0.305 lambda. And so now if we actually subtract this, what we end up with is 0.032 lambda. And this is LB. Okay, now we can do the exact same thing for LA. But the thing to note here, and this causes confusion sometimes, is some people might be tempted to say, okay, you know what, this is 0.165 here, roughly. This is 0.305. If I say 0.165 minus 0.305, I will have my final answer. It doesn't work that way, because the issue here is that once I go along this line back towards this, because keep in mind I'm going towards the generator, away from the load. So if I go in this counterclockwise direction, I start here and all of a sudden I get to 0 and a new cycle starts. So when you're crossing the cycle, it's difficult, well, it doesn't make sense to, at least, to subtract this point, because this is in a whole new revolution in terms of lambda over 2. So the best way to do this, the way I've always done these sort of things, is to always travel to that horizontal, or if you're on this side, travel to this horizontal, and then add the difference to it after. So I know that this distance from my starting point, load, to this part here, so what I'm going to do is, let's get rid of this green line just because we're not using it anymore. So if I start from my load and I go to here first, okay? We're going to break it up into 2 steps, that way we can add the 2 things directly after, as opposed to subtracting 2 points. That is incorrect. So here I have about 0.195, and this thing is 0. So if you use the middle scale in this case, you'll notice that this thing starts from 0 and it goes up. This is 4, 5, 6, 7, 8, 9, 10, all the way up to 0.195. So if I'm looking at the middle scale, that's actually 0.195. Therefore, in this case, this whole thing is 0.195 lambda. Now I want to, first I'll get rid of this. Now I want to add to that 0.195 this distance. Now what I'm going to do is I'm going to switch to the outer scale, because why? The outer scale is increasing. So this point is 0 for the outer scale, and all of a sudden this is 0.04, this is 5, 6, 7, 8, 9, 10, all the way up here, and this looks like it's about 16, or sorry, 0.165. So now this is going to be 0.165 lambda. Therefore, my LA is going to be the sum of these two. So LA is going to be 0.165 plus 0.195. Okay, so this will be 0.165 plus 0.195 lambda. Now, if I actually add these two together, I will get that this is 0.36 lambda. Now, suppose for a second somebody says, okay, you know what, I don't want to do it this way. I don't like this way. This way doesn't make sense to me. How can I do it your way? Or how can I do it one way no matter what? The thing to realize is if I'm going towards this generator, I cross 0 here, meaning I've completed one revolution. Why? Because this is 0.49 at this point here, and the next one is 0.5, and then it starts from 0.01 again, and it starts going up. So if I do subtract this point, let's say I take 0.165, so let's take 0.165, and I subtract from that 0.305, which is my point, which was my initial point. So if I do that, what I end up with is I get minus 0.14 lambda. First of all, a negative distance doesn't make sense to me, so I need to reconsider my answer. But the fact that I've crossed this 0 part, in order to get the same result that I got using this breaking up method, what I do is I add 0.5 lambda to take into account that I'm in a new cycle. This now becomes 0.36 lambda. So whenever we go into a new cycle, we need to add that 0.5 lambda to take into account that these results are actually in a new cycle. The Smith chart doesn't know we're going in multiple revolutions. We are the ones that actually go through and figure that out. So I always like to break things up in terms of going to the horizontal, just because that way you can actually read numbers off easily. Like if you look at this way, we read off the middle scale. Sorry, we read off the outer scale on the top, and we read off the middle scale at the bottom. So that way it kind of just, it makes it a little easier to see the number exactly, as opposed to having to subtract things out all the time. So that's just a little bit on actually, manipulating your way through the Smith chart. So we found there the distance between the stub and the antenna. So there could be two possible distances. Now we want to find the stub length. So the stub lengths are dA and dB. So now how do we find this? So if you go back to that Smith chart stub tuning methods video, you'll find that to find dA and dB, I need to take the distance from PSC. So PSC is this point. So I go from PSC to A prime. This is going to be dA. And if I go from PSC to B prime, that is actually going to be PSC to B prime. This distance here is going to be dB. So I guess the easier one to do, well, this is kind of messy. Let's clean this up a bit. So let's use this light green here. So this here, and we'll call this dA, is in green. Well, I don't like that at all now, actually. So this is going to be dA, and dB, we'll call this light blue one. And so you see here, now this is why I draw these lines on the outside, just because this way I can actually go out and realize that I'm still at that same point going there. And so I know which point I'm lining up with. So that's dB. So I should get rid of this so we don't confuse anyone either. So dA is the first point we're going to find. So on this side, we are at 0.25 lambda, always. And now at this point down here, looks like we're about 0.372 on the outside scale. So this is going to be 0.372 lambda on the outer scale. Then dA is just going to be that difference. So dA is going to be 0.372 minus 0.25 lambda. And so dA is going to be 0.122 lambda. Okay. dB is going to be, so if I traveled this half, I got 0.25. Now to get to here, I'm going to use the outer scale. That arrow's kind of in the way. So let me just get rid of that arrow for a second. So this is going to be B prime, we called it. And so on the outer scale now, because this side starts from 0, so I'm counting up here. On the outer scale, it looks like it's about 12.8, I would say. So I'm going to say that this is going to be 0.25 plus 0.128 lambda. Now if I add these two together, I will get 0.378 lambda. Now there's a really good way to check if you've done this problem correctly or not. And I don't think I mentioned this in the previous video on stub tuning, the foundation of it, but this is always true. I'll write here, note, dA plus dB is always going to equal lambda over 2. So if you found one, you found the other. Now if you look at this case, if I actually add these two things together, 0.122 plus 0.378 actually equals 0.5. And so I have satisfied that sort of law or condition. If it doesn't equal, you've done something wrong. So these are sort of simple ways to check out what you're doing. Okay, now the last part asks us for SWR on all segments. Now, how exactly do we figure this thing out? So there's really three segments, okay? We have, we're going to have a stub. We're going to have a part here that's going to go to the load. And then we're going to have the actual main line itself. and I'll draw it dotted here, just so it looks like it's actually on the other side. So there's 3 SWRs, because there's 3 interfaces, right? So there's going to be an SWR here, there's going to be an SWR here, and there's going to be an SWR here. So the SWR, we'll call this 1, 2, and 3. So SWR1 is between line and stub. So between the line and the stub, we should have the matched condition, correct? This means S equals 1. So this is matched condition, because the whole purpose of inserting the stub in the first place was to match the impedance of the stub to, or the impedance looking into the load to that of the line, right? What's next? Now we have SWR2 is stub, I suppose, because that's along the, we'll call it along stub, okay? So it's along the stub, and this is what? This is going to be infinity. Why? Because it's short-circuited, and we know that in a short circuit you'll have full reflection. Full reflection means SWR is infinity. So now here SWR3 is going to be between stub and load. Now this is the one that we can actually find without just reasoning what's going on. For that one, we go back to our Smith chart technique and we find this point where it intersects here. Now if you find that point where it intersects, I believe I see about 2.6. Should be a little bit higher actually. On my paper I have about 2.65, closer to 2.7. But according to this one, we'll call it, let's say, 2.65. And this is not radius, it's the intersection of S circle and real axis. So that third SWR is, I'm going to take this radius here, well, not even radius, I'm just going to take that intersection point. What is that intersection point? It's about 2.65-ish on my paper. It looks like it's about 2.6 here. That's just because the circle is probably off-center. Drawing it electronically is a little bit of a pain. But still, it conveys the entire idea, I believe. So that's it. We've gone ahead and we found everything. We found the admittance is YS. We found these two distances, LB and LA. We found the two possible lengths. And I guess we can also, well, let's call this 1, call this 2, and we'll call this 3, and this is 2.65. So now we've also found these SWRs on all of the on all segments of the line. You can call it S1, S2, S3, you can call it SWR1, SWR2, SWR3, as long as the person that you're trying to refer this to knows what you're talking about. It shouldn't be much of a problem. So if you have any questions, please leave them down below and we'll try to get back to you as quickly as we can. And other than that, I hope you found this video helpful. If you haven't already, hit that subscribe button and you'll know as soon as we have new videos for you. And besides that, we'll see you in the next one.